So we've just finished proving that if you hand me a collection of open sets, no matter how large that collection is, even if it's so infinite that our minds can't even comprehend it, that the union of infinitely many open sets is going to give us an open set. But that the same might not be true about intersections. If you hand me infinitely many open sets, the intersection of that infinite collection might no longer be open. We can only guarantee that the intersection of a collection of open sets remains open if that collection was finite. So in this video, I just want to revisit that with an eye towards the general picture of topology, and also along the way, figure out how we can make a similar conclusion about how closed sets behave under unions and intersections. So here was the big deal, right? That we know for sure that the union of any number of open sets is going to be open. Even if we have infinitely many open sets, that infinite union is going to remain open. But the same might not be true about intersections. The intersection, though, of any finite number of open sets will remain open. So in general, in point set topology, this thing right up here, this box, is actually how we define what it means to be open sets in the first place, right? We can build a sensible notion of topology, something that's able to kind of describe general notions of shape and size and closeness and distance without reference to distances and that kind of stuff. That topology is about specifying what subsets of a space get to be open sets, which collections of subsets behave in the ways that collections of open sets ought to behave. And this actually provides that characteristic behavior. Any collection of sets which behaves in this fashion, that the union of any number of them remains within that collection, and the intersection of any finite number of them remains within that collection, then we can call that collection a collection of open sets with scare quotes around it, right? Because it might not be the same as the ideas about interior points and epsilon neighborhoods that we have, but any collection of subsets of a space which is preserved under the union of infinitely many of them, as well as the intersection of any finite number of them. That collection can be called a topology on our space, and we're going to call the members of that collection open sets, even if they're not the same as the open sets that we've been looking at, right? So this is how in general point set topology we can sort of define what it means for sets to be open, right? Or a collection of sets to qualify as open sets. But then the other really, really useful fact that we had a couple of videos ago was that there was a relationship between openness and closedness that lets us transport ideas from open set land into their corresponding ideas in closed set land. And that idea was that openness and closedness are complements of one another. Closed sets are exactly the complements of open sets, and open sets are exactly the complements of closed sets. And so with that fact in mind, we can actually figure out how closed sets behave under unions and intersections. And the only ingredient that we need additionally in order to do that is to remember what happens when I take the complement of a union, or when I take the complement of an intersection. Those are the De Morgan laws for sets, right? The complement of the union of two sets is the intersection of the complements of those sets. And vice versa, the complement of the intersection of two sets is the union of the complements of those sets. So any notion that I have about unions of open sets, if I just take complements, I'm going to get the corresponding notion about the intersection of their complements, which are closed sets. So what that tells me, for example, is that because the union of infinitely many open sets even remains open, that also the intersection of even infinitely many closed sets is going to remain closed. So adding the De Morgan laws into this mix tells me that the intersection of any number of closed sets is going to remain closed, but that the union preserves closedness only if that collection is finite. We only get a guarantee that the union of finitely many closed sets is closed. So this is, again, the wonderful thing about having this complement way to go through the looking glass between open sets and closed sets, from one end of the spectrum of open to closed to the other end by taking a complement, right? And the great thing about that is that now we get this result about closed sets, starting from this result about open sets and having to do nothing else other than hit it with the De Morgan relations, right? So open sets are collections of sets where we can preserve that collection through infinite unions, and only finite intersections are guaranteed to preserve it. Closed sets, likewise, are collections that can be preserved under finite unions and infinite intersections. This is how, in general, point set topology is sort of the first, it's like lecture number 1 in point set topology, is this is what topology is. This is what open sets get to do. This is what open sets are supposed to behave like. And we can define lots of other funky examples of topologies on a set. Sets that, subsets of a set that qualify as open because they behave like this, but not necessarily because they have anything to do with epsilon neighborhoods or the other stuff we talked about. Right? So that is kind of where point set topology begins. It's where our study in real analysis is going to kind of end, at least as far as open and closed sets are concerned. What we want to do next is we want to push towards the more sophisticated sort of second level topological properties of sets. When we get beyond open and closed, what are some other really useful properties of subsets of the real line? We're going to talk most at length about compact sets. Compactness is probably the biggest deal. But we'll also visit other notions such as connectedness and perfectness and denseness that are especially valuable for helping to make our intuitions about functions and real numbers in analysis more precise.